Basenets and conditional probability tables. In the previous model, we explained how a causal graph represents a Bayes network, in which the joint probability distribution over the variables is factorized into a product of conditional distributions. Here, we will show how to express those conditional distributions as conditional probability tables. Let's use a simple causal graph relating education, income, and happiness. For this graph, the joint probability distribution is factorized into three conditional distributions: the probability of education, the probability of income given education, and the probability of happiness given education and income. We are going to define the variables in our model as categorical, meaning that we are constraining the variables to take on values in a finite number of categories. For example, consider first the variable education. Assume that education has two categories. If the person has not a college degree, we set the variable to 0. And if the person has a college degree, we set the variable to 1. Now consider the variable income as having two categories. If the person has an annual income above $45,000, we set the variable to 1. If not, set the variable to 0. Finally, define happiness as a variable with two categories. If the person reports that she is happy, set the variable to 1. If not, set the variable to 0. When the variables have two categories, as in our example, we refer to them as binary variables. For clarity, during the next slides, we will indicate, next to the notes in the graph, that the variables are binary, and express the factorization of the joint distribution, so we can follow how this information is used to build the conditional probability tables. In the conditional probability table for a variable, we will express in the columns of the table the values that such variable can take, and in the rows, all the possible combinations of values for all the variables in the conditioning set for this particular variable. Let's start with the first variable in factorization, education. As we can see in the causal graph, education does not have any parent, and thus its conditioning set is the empty set. When a variable does not have any parents, its conditional probability table will only have one row. And as mentioned before, the number of columns will correspond to the number of values that the variable can take. Education is a binary variable. Thus, the table will have two columns. One column for education equal to 0, and one column for education equal to 1. Next, we have to assign probabilities to each of the values that education can take. This is known as instantiate our model. As seen in the table, when education equal to 0, we assign a probability value of p. And given that the sum of the probabilities for all values has to be equal to 1, the probability for education equal to 1 is necessarily 1 minus p. For example, assume that education equal to 0 has a probability of p equal to 0.67. Thus, it necessarily has to be that education equal to 1 has a probability of 1 minus p equal to 0.33. In this case, where there are no variables in the conditioning set, the conditional probability table is known as the marginal probability table. Let's now build the conditional probability table for the variable income. From the causal graph and the factorization of the joint distribution, we can see that income has one parent, education, and thus one variable in the conditioning set. Furthermore, we also know that education and income are both binary variables that can take two values, 0 or 1. First, we determine that the conditional probability table for income has two columns, given that income can take two values, 0 and 1. Next, given that education is the only variable in the conditioning set, and education can take two values, the table will have two rows, one for each value education can take. When there is only one variable in the conditioning set, the number of rows will be equal to the number of categories a variable can take. Before assigning probabilities to this table, let's understand how to read its entries. The leftover entry is read as the probability that income has a value of 0, conditioning on education being equal to 0. The right downward entry will be read as the probability that income takes the value of 1, conditioning on education being equal to 1, and so on for the rest of the entries in the table. As mentioned before, each row in a conditional probability table has to sum to 1. So, to instantiate the model, consider the next assignment of probabilities. Finally, let's build the conditional probability table for happiness. This is a more intricate case because happiness have two parents, and thus two variables in its conditioning set. As mentioned before, the number of rows is determined by all the possible combinations of values of all the variables in the conditioning set. In this case, there are two binary variables, education and income. So we have to consider all the possible combinations between the values of the two conditioning variables and assign a row for each of these combinations. So the question is, how many combinations do we have for this case? To compute the number of combinations, we just need to multiply the number of categories of each variable in the conditioning set. In this case, education has two categories, and income has two categories. So 2 times 2 equals 4. We have 4 possible combinations. Thus, we have 4 rows in the conditional probability table. Finally, we instantiate the probabilities and check that each of the 4 rows sum to 1. So, for example, this conditional probability table tells us that the probability that happiness is equal to 1, conditioning on education equal to 1 and income equal to 0, is 0.25. In the previous graph, all the 3 variables were binary variables, taking 2 possible values, 1 or 0. But what if one or more of the variables have more than 2 categories? Consider the same castle model, but with the difference that the variable education can take 3 different values. 0 if the person has a high school diploma, 1 if the person has a college degree, and 2 if the person has a master's degree. The variables income and happiness remain the same. The joint probability distribution will be factorized in the same way, but now the conditional probability tables for each of the 3 variables will change. The conditional probability table for education now has 3 columns, given that education can take 3 different values, and as before, just 1 row, because education does not have any parent, and thus no variables in the conditioning set. As before, the probabilities expressed in the row need to sum to 1. For this case, we just need to define 2 values for the probabilities P and Q, and the third one will be immediately determined as 1 minus P minus Q. Let's instantiate the probabilities with the following values. In the conditional probability table for income, income is a binary variable, and thus the table has 2 columns. But now, education, the only variable in the conditioning set of income, has 3 categories, and thus the table has 3 rows, 1 for each value that education can take. We instantiate the table with the next values and check that each of the 3 rows sum to 1. Finally, consider the conditional probability table for the variable happiness. Happiness is a binary variable, and thus the table has 2 columns, 1 for each value of the variable. Now, to determine the number of rows, we have to consider all the possible combinations of values for the parent variables, education and income. As mentioned before, the number of rows is determined by the number of possible combinations, and this is obtained by multiplying the number of categories of each parent variable. For this case, we multiply the number of categories of education, which is 3, times the number of categories of income, which is 2. 3 times 2 equals 6 rows. As the number of variables in the conditioning set and the number of categories for each variable increases, it becomes more challenging to fill up the rows expressing the possible combinations. An easy rule to enumerate the combinations in an orderly fashion is to first choose any of the parent variables and divide the number of rows by the number of categories of the parent variable we choose. For example, if we choose education, which has 3 categories, we divide the 6 rows by the 3 categories, which equals 2. And to fill up the rows, we repeat 2 times each category of the variable education, as so. Next, we choose another variable in the parent set and divide the number of repetitions for each category we obtained in the previous step by the number of categories for the new variable. In this case, our next variable is income. It has 2 categories, and the number of repetitions assigned to each category of educations in the previous step was 2. So, 2 repetitions divided by 2 categories equals 1. This implies that we must repeat 1 time each category for the variable income and do it again until we fill all the rows. If we find more variables in the parent set, we repeat this process for each of the variables in the parent set until we fill up all the possible combinations of values for the parent variable. Finally, let's instantiate the model by adding probabilities for each entry, recalling that each row must sum to 1. To close this section, let's work through another example. Consider the next Castle graph with 4 variables, x, y, z, and w, in which we indicate next to the nodes all the possible values that each categorical variable can take, and also show to the right the factorized joint probability distribution according to the Castle graph. So, which will be the conditional probability table for the variable w? We start by computing the number of columns. In this case, we have 3 columns, because w can take 3 possible values, 0, 1, or 2. Then, we compute the number of rows, which is obtained by multiplying the number of categories for each of the parent variables of w. In this Castle graph, w has 3 parents, x, y, and z, each a binary variable with 2 categories, so the number of rows is 2 times 2 times 2 equals 8. We have 8 rows to lay out all the possible combinations of the parent variables. Next, to lay out the combinations of values for the parent variables, we start by choosing any of the parent variables. Let's choose the x variable, and divide the number of rows in the table, which is 8, by the number of categories of x, which is 2. 8 divided by 2 equals 4. So we fill the rows by repeating each category of x 4 times as so. Now we choose another variable of the parent variables. Let's choose y, and divide the result of the previous step, which was 4, by the number of categories for the variable y, which is 2. So 4 divided by 2 equals 2. This implies repeating each category for y 2 times, and doing it again until we fill all the rows. Finally, for the z variable, we divide the result of the previous step, which was 2, by the number of categories of the z variable, which is 2. So 2 divided by 2 equals 1. This implies filling the rows by repeating each category 1 time, and doing it again until all the rows are filled. To finish up, we instantiate the conditional probability table for w by setting values for the probabilities for each row, being sure that each row sums to 1.